Hey, pre-calc students, Mr. Mitchell here. Today, we're going to take a look at the tangent line question. Why we look at derivatives. We've learned about how to calculate a derivative. We really didn't talk about what a derivative is. So today, we're going to take a look at that. What's the point of a derivative and everything? So tangent lines can be used to describe the rate at which a curve rises or falls. So this is a parabola that's opening down. It does not have the same slope everywhere. It has zero slope at the top, and then it has different slopes as it goes down on each side. So you can see here's one positive slope over here. Here's a negative slope that's different, okay? The closer you get to the top, the smaller the slope gets, the less steep it gets until it gets to the top where it's zero. So on the one side, it's negative. On the other side, it's positive. It's a positive slope. As you go further down the curve, it gets to be steeper. It never quite gets to be an undefined slope where it's completely vertical, but it does, even if you go off the screen there, the curve gets steeper and steeper. Okay, so we're talking about tangent lines. And remember, a tangent line, if you think of a circle, because I think you learned this in geometry. If you have a circle, you have one place that a tangent line can touch it at. Okay, so that line only touches that circle at one place. Okay, so that's what we're talking about here. I know it looks like it touches it a bunch of places, but if we were to zoom in with like a microscope on that spot, it's only going to touch it at one spot. Okay, so trying to draw it a little bit better here, just with a circle. Again, you can have tangent lines of circles, you can have tangent lines of parabolas, you can have tangent lines of a lot of things. But it's only touching at one spot. And it doesn't cut through the circle and hit twice. That's called a secant line. Okay, so we're only touching it at one place. All right, unlike circles, tangent lines can meet curves in more than one point. You can still cut a circle twice, though, now that, but that's not what we're talking about, tangent lines, okay? So the slope of a graph, we call the tangent line to a curve at a particular point, the slope of the graph at that point. So what it wants us to do here, for this example, we have a parabola. We have a tangent line that intersects right here. And we want to find out the slope right here at that point. So here's your point. Find the slope. So we have to calculate the slope of this line. Well, if you have a graph, you can just count. So it looks like our slope is equal to, if I come over here, it looks like we are going, if we start here, this is -1, and it goes from here to here. Looks like it crosses there and touches there. So if we count up 1, 2, 3, 4, and we go over 1, that's a slope of rise over run. And so then my slope is 4. Okay? So that's kind of what we're doing. Secant lines approach the tangent line. So here you have a bunch of lines that are secant lines. So we're trying to find the slope at a particular point. Okay? So if you do a bunch of secant lines, and again, a secant line can touch at 2 different places. Tangent lines aren't allowed to touch at once. So we're trying to find the slope here at this particular place. So if you draw a bunch of secant lines, they will approach the tangent line. They will get close. Well, when you say approach, the word approaching kind of leads us into a limit. Okay. So technically, this is a limit, and it's the limit of the tangent line, which leads us into a derivative. Okay. This is actually the formula for a derivative to do it by hand. We're not going to do that in our class. That's something that you can do when you go to regular calc, but that's technically the definition of a derivative. It's the limit as h approaches 0 of this, okay? And it comes from the secant lines approaching the tangent line. Again, the word approaching, we're approaching something, okay? So let's take a look at another example. Find the slope. So let's put this into practice. So find the slope of the graph, y equals x squared plus 1. So notice I have no place to draw a graph. I don't have my calculator pulled up, and I'm not going to. So could I graph it and find the slope by counting? Absolutely. but there's another way. What if we find the derivative of this and then we plug in our x value? Because isn't that kind of what we did up here for this problem? Didn't we find the slope at this point? Okay. We found the slope at 1. We really didn't care about the y value. We just needed to know x where to start, and then we went up and over to figure out our slope. So that's the same thing we want to do down here, except for we're not doing it in a graphical way. So let's find the derivative. So we can call it y prime. Talked about f prime of x. You can call it y prime. That means derivative. Again, different ways to write the same thing. So we want to find y prime of this. So how do you find the derivative? Well, you take your exponent times your coefficient, keep the variable, and then take one away from your exponent. And so that's to the first. And then when you take a derivative of a constant, it's just, I'm not sure why it's doing that, but we'll just have to deal with it. So there's your derivative. 2x. So now we're going to take our 1 and plug it in. So the slope of the tangent line at that place, the derivative is 2 when you plug in the 1. So what that means is at that particular point, at 1, 2. So if I make a graph at that spot on my graph, the slope of the tangent line is 2. Again, not because of this 2. All right, maybe not a great example to start here, but that's what it is. If we want to try another point to show an example, let's try to find the slope of the tangent line at 4, so if you plug in 4, you get 17. Okay. 4 is on the graph. Let me erase some of my scribble scrabble here that's getting in the way. Oh. Again, not sure why the pen is acting goofy. Oh, there we go again, it's acting goofy. So that was just the answer of 2. So now we're going to find 4, 17, the slope of the tangent line at that place. So all you do is take your derivative. Again, not sure why it's doing that, but it is. Take your x value 4 and plug it in. So the slope of this is 8 from this point. Notice 17 has nothing to do with it. Really, the y value does not play a role in finding the slope of the tangent line. Okay, so let's find the slope of the graph at this place. So here the notation is f of x. So we need to find f prime of x. And so we take our 2 of our exponent times our coefficient of 2. And so that's 4x. The 3 does nothing. Okay, so here's our derivative. And then you say, well, it didn't give us a point. I know. It gave you x and then f of x. So this is the slope of the graph everywhere. This is the derivative everywhere. This is the slope of the tangent line everywhere. So if they don't give you a point, that just means you're finding the derivative. You're not actually plugging in a number. Okay. If they give you a specific value, then you plug it in. If they don't, then you don't. So this is the slope of the tangent line everywhere. Okay. So the slope of our graph is 4x. So that's not a number that we're used to as rise over run, but it is the answer in general for this. So that's what a derivative is. Okay. So we talk about derivatives. So the way you can show a derivative, you can say y prime, you can say dy over dx, you can say d over dx of f of x, you can say d sub x of y. And you can also call it, we've talked about this before, you can call it f prime of x. Any one of those works. It's more of a preference, okay? When you're writing it, you get to choose. When you're reading it, you just have to be able to interpret. There's different ways of writing it, okay? So a couple more derivative practices here. So find the derivative of the following. So we're going to take our exponent times our coefficient. So when we do that, we're going to get 2x. All right. And then we're going to take the derivative. You take one away, it's just 2x. Now we take the derivative of x. Well, there's a 1 here times the 1 out front. And that's just a 1. And then you take the derivative of -2, and that's just not there. So this is the derivative. It's the slope of the tangent line everywhere. Okay, that's what a derivative is. So now we're getting into not just finding derivatives. Now, what do they mean? They're the slope of the tangent line. So here's my parabola. The derivative is the slope everywhere along that parabola. You don't have a specific x value to find. It's just everywhere. If you find or ask a certain value, then you can find it by plugging it in. Okay, so for letter B, again, we're finding the derivative. We need to change it and pull it on the top. So it's going to be x to the -1. Okay, got to pull it on the top to find the derivative. So I do that. So now we're going to take our exponent times our coefficient. So that's going to be a -1. We keep our our variable. Take 1 away from -1. So if I owe you $1 and I borrow 1 more, that means I owe you 2. And then that's it. But now we do need to simplify. So I'm going to leave the -1 on the top. I'm going to put my x on the bottom. And when I do that, my exponent becomes positive. So there is my derivative. That's the slope of the tangent line everywhere. So if you graph this, this is the slope everywhere. If you wanted it a specific place, they have to give you a specific number, x. The y value, again, doesn't really matter. You need that x value. If they don't give you a specific x, then you're just finding the derivative, and it's the slope of the tangent line everywhere. Okay? Let me know if you have any questions.